Hi folks, my name is Juan. I am the founder and AI automation lead at Statica Flux. In this video, I'm going to show you how to design and deploy SOC 2 compliant AI systems, giving you an edge by leveraging AI apps to the level and security and trust that top SaaS companies use, now apply to large language model infrastructure. If you're an enterprise or you are in fintech looking to integrate AI systems into your stack, this is the video for you. In this video, we will cover the cloud architecture through AWS and network engineering aspects of developing an AI system that is SOC 2 compliant. We will reserve the AI, software, data, and computer engineering aspects of an AI SOC 2 compliant system in other videos. SOC 2 is a cybersecurity and data privacy framework created by the American Institute of Certified Public Accountants. It defines how organizations should securely manage customer data. It's a framework to protect customer information against unauthorized customer information access, data leaks, and operational failures. SOC 2 is built around 5 trust service criteria. 1. Security, which is protecting against unauthorized access to the data. Availability, ensure uptime and workability around the clock. Processing integrity, guaranteeing data accuracy. Confidentiality, which keeps sensitive data private. And privacy, which handles personal information in accordance to internal organizational policies and legal regulations. For AI systems, SOC 2 isn't optional anymore. If your LLMs touch sensitive customer data, you must design for trust, security, and transparency. We have 2 types of SOC 2. Type 1 verifies controls exist and are properly designed at a specific point in time. Type 2 verifies controls work effectively over a period of time, typically 6 to 12 months. The SOC 2 audits are performed by independent third-party CPA firms that are licensed and registered with the American Institute of Certified Public Accountants. These firms specialize in IT assurance and cybersecurity audits, and these are the only entities authorized to issue an official SOC 2 attestation report. SOC 2 compliance is as much about visibility as it is about controls. So I maintain independent logs across applications, databases, network logs, system logs, and authentication processes so that I can trace when something went wrong. If I have this comprehensive set of logs, I can trace who did what, when, and how within seconds. How does SOC 2 compliance apply to AI applications and systems? With the advent of LLMs to help process data, we have the rise of inference engines, which are a set of logical rules, usually materialized through agentic systems, to process data through LLMs and other AI models that automate insights, decision-making, content generation, etc. And so in order to maintain utmost privacy for clients, a lot of organizations, particularly in the financial industry, are now hosting these inference engines in their premises or in cloud-based solutions. So the trust service criteria still applies to inference engines. Security means LLM endpoints must be protected against unauthorized access or prompt injection. API keys, access tokens, and embedding stores must be encrypted. Availability means that the inference engine needs uptime monitoring, failover plans, and scaling policies to ensure customers can rely on the model. Processing integrity means that we need to monitor the performance of the model, and the model should process input accurately and predictively. And this means implementing guardrails, validation logic, and version control to detect anomalies. Confidentiality means sensitive user data sent to an LLM is encrypted in transit between the different servers instances within AWS. And privacy means that if the LLM can learn from the stored user data, you must disclose this in your privacy policy and ensure data decision retention controls exist. When I create a cloud architecture for a SOC 2 compliant financial application, I dedicate a whole virtual private cloud, which is going to be the isolated virtual network in which you can recruit whatever computational resources you need, and you set the network rules, boundaries around those computational resources and how they communicate with each other. So in this one, you see that we have 3 computational resources, which in AWS lingo, it's called instances. And then aside from that, we have subnets. Within the VPC, you can create sub networks to segment networks from each other and therefore decrease the likelihood of compromising the whole VPC if one computational unit instance is compromised. For public subnets, we have route access to an internet gateway, which is a component that allows the VPC to communicate with the internet. And this is most common for web applications or load balancers that you want your customers or the internet-based clients to have access to. While a private subnet does not have access to this internet gateway directly, which effectively isolates the resources within the VPC. And this is usually used for database instances, which has the most sensitive client information. And what do we mean by instances? Well, within the VPC and the segmentation of networks through subnets, we have the computational units, which within AWS lingo are called EC2 instances. This is the fundamental computational unit for AWS. And as the fundamental computational unit for AWS, it gives you the most ample, wide, flexible, and comprehensive server unit that AWS has at its disposal within its resource ecosystem. This is the reason that I rely on EC2 instances to create and deploy my inference engines. This goes back to a system design theory axiom. Simplicity is giving up control. If you want control, the more complexity you have to accept. And on top of this, what you can do is to connect your Windsurf or whatever agentic IDE you want to use through a safely encrypted SSH connection to your EC2 instance in order to increase your productivity in terms of coding at a lightning speed. By connecting through your agentic IDE to the EC2 instance, you have control, speed, and testability. And what I mean by testability is nothing more than having an EC2 instance, which is a perfect environment to test for launching the application at the production level. And the reason that this is the ideal place for doing so, specifically for the AI engineer who's going to be connecting through our agentic IDE or whatever IDE is of your preference, is that you're going to be able to test your LLM engine in a Linux operating system that is identical to the production environment. You can set up the network that allows all instances to communicate with each other, including the database. So you can have live databases, streaming data, and edifying a rack system that retrieves that information depending on the needs of the clients. And then, of course, software integrity, no more unnecessary fragmentation of microservices. The CI/CD pipeline can customize, can be containerized, and the whole infrastructure and inference engine of our software can be deployed into a production auto-scale group whenever we want to through GitHub Actions or whatever other CI/CD tool you want to use. And this is the most important aspect for AI engineers. You can actually pick the computational resources that are needed for your inference engine. And what I'm talking about here is picking the right EC2 with enough gigabytes in VRAM, deciding whether you want to use an A10 or an A100 NVIDIA GPU, how many gigabytes you want it to have. If you want to do CPU offloading, then of course you can also observe how much CPU capacity the EC2 instance has. And then, of course, deciding the resources that you're willing to pay for in order to have any specific models being deployed in your EC2 instance. If you're deciding to deploy a small model, an 8 billion parameter, then perhaps an 810 NVIDIA GPU is enough. If you're basically striving to have a 1 trillion parameter model, then perhaps a bundle of 8 100s is going to be enough for you to be able to have your LLMs being deployed in an EC2 or an automated scale group if you're already at the productionalized level. Usually in an AI app, aside from the inference engine, you have a database and another instance for hosting the app. The ideal networking setup for the SOC-2 compliant AI system is that you host all 3 instances in separate private subnets. And the reason is because we want to exercise the principle of network segmentation, in which we divide the VPC network into smaller isolated zones, which are our subnets, and we maintain minimal necessary communication between all instances so that we can reduce the attack surface on the network. If one server is compromised, the attack can't freely reach the database or other managed instance resources within the VPC. So that is, we don't let everything talk to everything. So as you can see right here in my diagram, I have a private subnet specifically for the inference engine. I have another private subnet for the application, and then a DB subnet for the database. And what I mean by a DB subnet is simply meaning a private subnet with 2 availability zones, because usually databases need 2 availability zones just in case one zone goes down. Then the data can safely continue to exist in another availability zone. And then aside from the principle of network segmentation, I also practice the principle of least privilege, which, if we're having each user, system, instance, and processes, you have them only at the minimum access rights and permissions necessary for those resources to perform their specific tasks and nothing more. And that is, we don't give a blank access just in case. You grant what's required for exactly as long as needed, and then revoke and limit it. In our networking, I set only 1 port entrance for only necessary servers / instances, and then the communication between each server is encrypted, even if it's in the same VPC. Now, we already talked about how the inference engine is localized in a private subnet. But the fact that it's in a private subnet doesn't mean that it's completely suffocated from public internet access. In fact, we can create a bridge for the inference engine living in a private subnet to communicate with the internet through a network address translation gateway, a NAT gateway, which is a component to enable instances and private networks to initiate outbound connection to the internet while preserving inbound connections from the internet. And the NAT gateway is hosted in a public subnet, as you can see right here. And from the public subnet, it communicates with the internet through the internet gateway to be able to perform a lot of functions necessary for the AI engineer. Now, let me ask you something. Why do we want the inference engine instance to still be able to communicate with the internet? Why do we allow outbound initialization only? Well, we still want access to the internet because an AI engineer still needs to download dependencies or models from the internet. And the reason that we go forward with outbound initialization only is because we don't want unrequested internet access that the AI engineer cannot control. Like I mentioned before, all communication between the different instances must be encrypted. In this example and in the architecture that I designed, my inference engine communicates with the database through an SSL encryption. And it communicates with the web application EC2 instance through an HTTPS encryption. The database, which is hosted inside a private subnet, can easily communicate with all other instances by an SSL encryption. The web application can arguably be placed in a public subnet, since it's the EC2 instance which needs to interact with the clients who are going to be connecting to the web application through the internet. But a more secure method is to essentially have the application load balancer being hosted in a public subnet while maintaining the EC2 instance, which has a web application in a private subnet. And then from there, of course, the client communicates through AWS API Gateway, DNS, and from there it communicates with all the other instances through safely encrypted methods. So through my AWS architecture, I display how you can show customers that your AI systems meet the same rigor as your SaaS. And by doing so, you stand up in a market that is inherently distrustful of AI. And trust becomes your competitive edge. Those who adopt SOC-2 in their AI systems will win lasting edge in technique and customer trust. So by creating a comprehensive and secure AI system in an environment where AI is still mysterious, you will be dominating. At Statica Flux, I help companies in the finance industry deploy AI systems that are effective at automating workflows. These workflows are secure without inhibiting their dynamism. The AI systems can be audited and they are built to last. If you want to bring AI to your organization without compromising compliance or trust, feel free to book a free strategy call, link in the description. Also, if you want to stay updated with my latest work, my LinkedIn is right in the description as well. Thank you and see you on the next one.